Chapter 1 begins vector spaces. The calculus of several variables unites the calculus of one variable with the theory of vector spaces, and how well it goes depends on how thoroughly that theory is used. So the first two chapters study vector spaces themselves. We start from the geometric vectors the reader has probably met, arrows drawn from a chosen origin. Two of them are added by the parallelogram rule. Build the parallelogram having the two arrows as sides, and the diagonal from the origin is their sum. Vectors can also be multiplied by numbers. Multiplying an arrow by x gives another arrow along the same line, whose length is the absolute value of x times the original. It lies on the same side of the origin when x is positive, the opposite side when x is negative. These two operations satisfy certain laws of algebra. The book warns that geometric proofs of them are sketchy, more plausibility argument than airtight logic. The usual proof of the associative law is a picture of a parallelepiped and its diagonal from the origin. Another system the reader may have seen is coordinate triples. Here a three-dimensional vector is an ordered triple of numbers, and both operations are defined algebraically, entry by entry. The vector laws are much easier to prove here, since they are almost formalities. If we think of a triple as a function whose domain is the integers from 1 to 3, with the ith entry the value at I, then this example suggests a much more general type, called a function space. Now the definition. Let V be a set carrying an addition and a multiplication by numbers. The first four axioms concern addition alone. It is associative, it is commutative, there is a zero that changes nothing, and every vector has a partner summing to 0. The last four tie in the scalars. Multiplying by two numbers in turn is multiplying by their product. Sums distribute both ways, and multiplying by one changes nothing. From these, the 0 is unique, each negative is unique, and 0 times any vector is 0. The book's standard example. Take any set A and look at all real-valued functions on it. Two are added pointwise, and one is scaled by scaling its value at every point. Taking A to be 1 to 3 returns the triples. Taking A to be the line gives functions of one real variable. Now subspaces. Take a non-empty subset of V closed under the two operations. Then it is a vector space in its own right. The laws holding for all elements hold automatically in the smaller set, and closure keeps the 0 and the negatives inside it. So the continuous functions on a closed interval form a subspace of all real-valued functions there, and such a subspace is called a function space. The book takes vector spaces to be real, but replacing the scalars by complex numbers, or by any field, leaves most of it standing.